So, yeah, we're moving on to chapter 4. First, I will remind you to keep working on all the end of chapter exercises at the end of chapter 3. I'll put up the solutions soon, and indeed I may dip back into some of the exercises in lectures to talk about some of these results. Some of these are actually interesting results in themselves, particularly questions 10 and 11 I want to get to as well, and talk about those. But today, at least the first part of today, we're going to move on to chapter 4, which is the congruence relation. Now, you've already been exposed to bits and pieces of this. John has already been making use of it in the cryptography lectures, I believe. Okay, but we're going to approach it very carefully and set up the theory of the congruence relation very carefully and prove the important things about it. Okay? So this relates to the process of integer division with remainder. Okay? That we've already been doing, and we've already seen one good use of that from the tutorials last week. So recall, from tutorials we proved that p squared plus 2 is never prime for primes p, except for the single case of p equals 3. So except for that very initial case, which is somewhat of a special case and easy to check, 3 squared plus 2 is 11, which is prime. Every other prime number does not produce another prime number when you look at p squared plus 2. It's not immediately obvious by any means. Okay, and I'm not going to run through the proof again, but we proved it by considering dividing p by 6. And when you divide p by 6, well, 6 is going to go in some number of times into the prime, and it's going to leave a remainder, which normally the remainder you'd expect, if you're talking about things in general, you'd have to allow for remainders of 0, 1, 2, 3, 4, 5. But we arrived at the conclusion that, well, if we're looking at a prime number, in general, prime numbers can only leave remainders of 1 or 5. Okay. Remainders 2, 3, and 4 are excluded because they would imply that this number p is divisible by 2 or 3. So except for the special cases of the early primes 2 and 3, every other prime number, every large prime number, can only be written as a multiple of 6 plus maybe 1 or maybe 5. And by considering these cases, we were able to show that p squared plus 2 is always divisible by 3. Okay? So this shows the utility, or it's one example of the usefulness of this approach. Yeah, question? Yeah, good point. Considering.
Sorry.
No, that's perfectly pretty bad one. Considering that. Okay. So it's kind of useful, and you've started to see how it might be extremely useful in cryptography. So a basic way of encoding textual information, not encrypting it, just encoding it, is to simply translate each letter to a number. A goes to 0, B goes to 1, C goes to 2, Z goes to whatever it does. 23 or 25, how many letters are in the alphabet? I was corrupted as a youth because I just don't know how many letters there are in the alphabet, because there was a joke going around the playground, is how many letters in the alphabet. And how many is there?
26.
There's 26, but when you said that, the person said no, 24, JR was shot. And then someone else, JR is a character in the TV soap opera Dallas, who was famously shot and gotten rid of. And then another person was saying, no, it was only 22 because ET went home. So ET went home and JR was shot. So because of those jokes at an early age, I'm never sure how many letters there actually are in the alphabet. So my mind has been destroyed for that reason. So the letters can be encoded with numbers, and then we can encrypt by building our encryption schemes using mathematics. And the two primary things we can do with integers are to add them and multiply them. Okay? But ultimately, we want to turn the information back into textual information, encrypted textual information. So we want to stay within the system of low integers, 22, 25. Okay? So we work modulo 26. You can have So having a system of integers where you're only considering these low integers and the operations of addition and multiplication operate on that closed set, that gives you a context and a location where you can exploit mathematical properties of those operations and related ideas to build cryptographic systems. So let's jump right in and look at the basic definition. Definition 4.1, this is the congruence relation. So we consider any pair of integers A and B. We're going to consider n is going to be our modulus. And we say A is congruent to B modulo n. That's what we say, and we write it as A congruent to B modulo n. Okay, we do that to mean that n divides the difference A minus B. Okay, so the difference between the two, so we're defining this new thing in terms of things we already know. We already know about the divisibility relation amongst the integers. What we're defining now is a new relation, the relation of congruence. Congruence modulo n, okay, where n is any positive numbers. We say two integers A and B are congruent if their difference is divisible by n. So n is referred to as the modulus. And we write A is congruent to B modulo n. If this is not the case, i.e. n does not divide A minus B, we say A is not congruent to B modulo n, and we can write that as A not congruent to B modulo n. Okay. Sorry? If this is not the case. So if the n does not divide A minus B, then we say A is not congruent. Okay. So let's quickly look at some examples. E.g., 5 is going to be congruent to 5 is going to be congruent to 11 modulo 3, say. (22) is going to be congruent to minus 5 modulo 3. Okay. Differences between these quantities are divisible by 3, okay, because in both cases this 5 minus 11 is minus 6, 3 does divide minus 6, you can write minus 6 as a multiple of 3, 22 minus minus 5 gives you 27, so 3 does divide 27. Okay, and then negative example, well, 7 is not congruent to 8 modulo 3. Difference between them is minus 1. 3 does not divide minus 1. So there's some positive and negative examples. Straight away we can look at Theorem 4.1, which gives us an alternative view of the definition, and in some ways is maybe a better way to think about it, maybe. And this makes the link explicit between this new relation of congruence and the process of integer division with the remainder. Okay? So for a given modulus n, A is going to be congruent to B mod n if and only if A and B leave the same remainder after division by n. Okay, so if you do the process of integer division with remainder of A and B, dividing them by n, they're congruent if and only if they leave the same remainder. Okay. And we're talking here about where we can write A as, say, Q1 times n plus R1, B is Q2 times n plus R2, where these remainders R1 are both R1 and R2 are both bigger than or equal to 0, but strictly less than n. So we're talking about the case where you've got the proper remainder, the smallest non-negative remainder. So what we're saying here is basically that they're congruent modulo n if R1, if and only if R1 is equal to R2. Okay. So A and B are congruent modulo n if and only if they leave the same remainder. Now the proof of that is fairly straightforward. It's written out in full in the notes. We'll pass over it for the moment. I think I'll leave you to read that proof yourself, understand it. It's fairly straightforward. It just works off the definition of congruence that we just introduced. In fact, some people might even take this version here, the fact that the remainders are the same. Some people might even take that as their definition of congruence. It's a very good way to think about it, and for some people that would be the definition as well. Okay. Any questions so far just about the definition? Now, as I say, this idea lies at the heart of almost all modern cryptography, or a large part of modern cryptography. So we want to get the foundations very, very secure, and that's a good way of thinking about it. So there's a section here on equivalence relations. Equivalence relations you might have met a little bit in your first year, but I think for a lot of people this might be the first place where they look at them in detail. Okay? So congruence is what's known as a binary relation. Congruence mod n is a binary relation. Binary refers to the fact it's got two inputs. Okay, it's a binary relation. You could have a tertiary relation, you take 3 inputs, a quaternary relation or something would take 4 inputs. A unary relation would just take 1 input. And well, what exactly do we mean by a relation? Well, it's a formula, if you like. But it's not a formula that gives you another, like, numerical quantity or that. It's something that gives you a logical value. It's something which is true or false. Okay? So it's if you like, it's a function on 2 inputs. It's a function on 2 inputs with a logical value. And at least in the classical sense, there are only 2 logical values, true false. People do study kind of crazy more abstract logics where there's many truth values in kind of abstract philosophy or foundational consideration. But for us, we'll just operate classically. Everything is true or false. Every precise mathematical statement can be considered to be true or false. Okay? So saying A is congruent to B modulo n, it is clearly a relation. It is clearly something which is true or false because it is the case that n either divides the difference A minus B, that's the definition, n either divides the difference A minus B or it doesn't. Okay? It will be true or false. Okay? Now, there are many relations in mathematics that you can put on sets, okay? But of primary importance in mathematics are so-called, well, maybe primary is a bit debatable, but of some importance in mathematics are so-called equivalence relations. And an equivalence relation is a relation which, in a strong sense, it acts like the relation of equality. Equality is kind of the most important relation. Two things are related if and only if they're the same thing. But there are a lot of interesting relations, such as congruence that we're about to see, which act like the relationship of equality in a strong sense. Okay? So definition 4.2 is the definition of an equivalence relation. Now, quite often when we're discussing relations in the abstract, general relations, the character we use for the relation, just as we've used the three-line equal sign, if you like, for congruence, the character for describing just an arbitrary relation is a tilde. Okay? So a relation tilde, which is this character, those keywords, well, in this keyword, it's just both the hash symbol, tends to move around on American or UK English keyboards. It's this symbol, the tilde symbol. A relation tilde on a set X, probably need X to be non-empty, I guess, to be anyway interesting, is an equivalence relation. Means, so there are three parts to the definition, three very meaningful, important properties that a relation might have. Okay, so the first one says for every element X within the set, X is related to itself by this relation. So the statement X tilde X is true. This is called reflexivity. So the relationship is reflexive. Everything is related to itself. Symmetry says that, well, if X is related to Y, that implies Y is related to X. That's called symmetry. Symmetric. If I'm related to you, you're related to me. That's that property. And the third one involves three elements. And it says, if it's the case that X is related to Y, and it's the case that Y is related to Z, these two statements together imply that X is related to Z. If you like, Y is like an intermediary between X and Z. X is related to Y, Y in turn is related to Z. Well, if that always implies that X is related to Z, then we say that the relationship is transitive. This is transitivity. going to turn out that our relation, congruence, that we just introduced, is a equivalence relation. It does satisfy all of these properties, which is nice. So an example of, say, some that aren't, for example, if you consider the relationship of greater than on the integers. Greater than is a relation. It's a binary relation. You give it two inputs, this is greater than that, and that statement has a logical value. It's either true or false, depending on whether this is greater than that or not. So it's a binary relation. Is it reflexive? Is greater than reflexive? It's very unreflexive, really, because for every integer, x is not strictly greater than itself, okay? So it's not reflexive. Is it symmetric? No. It's not either. If x, y are in z, and x is strictly greater than y, then clearly y is not going to be greater than x. So it's not symmetric either. Is it transitive? Yeah, it is transitive. Okay. If A is bigger than B, B is bigger than C, yeah, A is bigger than C. Okay. But for all A, B, C, and Z, A bigger than B and B bigger than C does imply that A is bigger than C. So it is transitive. So in general, a relation may or may not have some combination of these properties. Particularly bad, particularly unstructured relations might have none of them. Something like greater than has two of them. Greater than or equal to, if you weakened this a little bit and said greater than or equal to, then it would be reflexive. Still wouldn't be symmetric. Still wouldn't be symmetric. Would still be transitive. Okay, and our equivalence relation our congruence relation will turn out to be an equivalence relation. Before we go and prove that, we're going to prove, well, why might we worry about equivalence relations, or why might we give them such attention? Equivalence relations produce what are known as partitions. Okay, partitions of the set. Now, what do I mean by produce? So we have the notion of an equivalence class. The equivalence class of an element x with respect to the relationship of tilde is the subset. Okay, we normally might represent it by putting square brackets around x. It's the subset of x, so it's every y from x such that x is related to y. So around every element, you gather around it and kind of parcel up with it all of the elements to which it is related. Okay? So we pick an element x, and we go out and we find all the little y's from the set that are related to x, and we bring them all together and we put them in this set called the equivalence class of x. So that's a fundamental idea. And then we have the definition of what a partition is. We have some sense of the word just from English, partition. Important concept in international relations, when countries get partitioned. Sudan was partitioned recently into North Sudan and South Sudan. Ireland was partitioned a while ago into Northern Ireland and the Republic of Ireland. India was partitioned at one point as it was gaining independence into India and Pakistan. Now, if you're gonna, it's easier to draw a picture of a partition. If you're going to partition, say, an existing country and split it into smaller countries, this is where maths can get political. But if you're going to do that, if you're going to take a large country and split it into smaller countries, if you're going to do, any kind of a good job of it, there are certain things you want to do. So you might draw some borders between different parts of the country. So you split it up into a system of subsets. So in the thing here, we call it a family P of subsets of X. Let's call them subset. Well, see, if I start labeling them S1 and S2, that automatically implies there's kind of finitely many or countably many. But what the hell? So you've got a system of subsets. Now, it'd be really bad if, in international affairs, if you make two of them have a non-trivial intersection. Because what you'd be doing, what you'd be saying is, this bit of land over here, well, it's going to be in this country, and it's also going to be in that country. That's a recipe for confusion at the very least, or conflict, probably. Some piece of land to which two countries lay claim, that's kind of bad, okay? So, you would want your subsets to be disjoint. Different subsets should have no intersection. Okay. Also, if you were splitting up a country, you wouldn't want to forget about any patch of land. This patch of land over here, well, that's nowhere. People living there are without a state, and nobody controls that land. Okay? Well, that is in international politics. That's probably a recipe for conflict as well, because different countries will probably try and lay claim to that non-claimed piece of land. Even somewhere like Antarctica, even though nobody's living there, but it has been divided up amongst the countries with interest in it, the countries close to Antarctica, and countries who first got there. So bits of it have been not made part of the other countries, but put under some kind of control. It's a series of lines that emanate out from the southern pole, I think, to the coast. And this bit belongs to Russia, or under the care of Russia, this bit. So those two fundamental ideas, your different subsets, you don't want them to overlap, and you don't want any bit to be unaccounted for. Okay, so these two conditions are in the statement that P covers X, meaning X is the union over all the subsets S and P, the union of these subsets. There we're using the union sign, just like we do capital sigma for big summations or capital pi for big products. We're talking about big union. These objects S, the description of them is every S in P. P is the family of subsets. So the partition covers X, and P consists of disjoint subsets of X. The way that that's kind of encoded formally is in this statement here: for every S and T in P, if S and T happen to have a non-empty intersection, so this says S intersection T is not equal to the empty set. If that's the case, then that's going to imply that S equals T. So the only time that two subsets can have a non-empty intersection is if, in fact, the two subsets are the same. we weren't really looking at two different subsets, we're actually looking at the same subset. Or another way to think about that condition, equivalently, you can say S equals T, or S intersection T is equal to the empty set. And that's maybe a more natural way of saying it, but that state, I mean, ors between two statements can always be turned into implications. If you say A or B, you can always encode that by saying not A implies B. It's an equivalent statement to A or B. And the key linkage between partitions and equivalence relations is that really they can be seen as just two different views of the same thing. If tilde is an equivalence relation on X, then P, which is equal to the system of equivalence classes, so P is the family of equivalence classes with respect to that equivalence relation, then this partitions X. And on the other hand, if P is an existing, if you already have a partition of X, then P induces an equivalence relation on X. Go back to our country analogy. Think of X as a country. The elements of it are loads of people, individuals. If you suddenly partition the country, you've then got an equivalence relation. The equivalence relation is I'm equivalent to you if we are both in the same new country. We are both in the same subset. Okay? So the equivalence relation induced by a partition is that little x is equivalent to y, means x and y are elements of the same subset. The same subset from P. So x is equivalent to y if you find them in the same subset of the partition. That's an equivalence relation. So that's the linkage between the two. So this is all general, talking about general, some notional relation on a set. If it satisfies these properties, reflexivity, symmetry, transitivity, give it a special name, we call it an equivalence relation. And then we have this related idea where you can take a large set and subdivide it into smaller subsets in a clean way, so that two different subsets have empty intersection, and you've taken account of everything in X. Everything is in one of the subsets. So these two notions are kind of equivalent. If you have an equivalence relation, it creates a partition. The subsets are the equivalence classes of the relation. On the other hand, if you have a pre-existing partition, underlying it, you can create an equivalence relation underlying, where you say two elements are equivalent if you find them in the same subset. Okay? So Theorem 4.2 brings this back to our new relation of congruence, and here we show that, and we will talk through the proof of this, that congruence mod n is an equivalence relation. So it nicely splits up Z. It nicely splits up Z, and we can draw a picture of it here. Now we're going to be talking mod n, the congruence relation modulo n. it's going to split up Z into a collection of subsets, and they are going to be the equivalence class of 1, well, the equivalence class of 0, the equivalence class of 1, equivalence class of 2, equivalence class of 3, and the kind of last distinct one will be the equivalence class of n minus 1. Except when we're talking about the congruence relation, the subsets, which are the equivalence classes, equivalence classes is a general name for them. If we're talking about the relation of congruence, we call them congruence classes. So equivalence relation is our equivalence classes is a general term, but they're called, when we're talking about congruence in particular, we'll use the name congruence classes. So the picture is that your integers mod n are subdivided into n different subsets. And these correspond to the congruence classes of the small positive remainders that you get after you divide any integer by n. Okay? So when you divide any integer by n, it's going to have some small remainder, so it'll be in one of these subsets. And we'll prove formally now that everything, that those three properties of the equivalence relation are satisfied for the relation of the congruence. So first of all, we let x be an integer. We know that n will divide 0. So we need to be talking about a modulus here. So we let n be an integer and n be bigger than 0. Okay, we know 0 is divisible by everything. That's one of the very first things about divisibility that we proved. Because 0 can be written as a multiple of anything. 0 is 0 times whatever the thing is. So 0 is 0 times n. So n certainly divides 0. So that implies that n divides x minus x. And by definition, that implies that x is congruent to x mod n. Okay? By the definition of congruence. By definition. So congruence mod n is reflexive. Okay, comes out pretty clearly. Secondly, if we let two integers x and y be in z, and we assume that x is congruent to y mod n. Okay, now we're trying to prove symmetry. So we're trying to conclude that y is congruent to x mod n. Okay, but the way we define congruence does make a difference. What's the element on the left and the element on the right. The way we defined congruence was that n divided the difference x minus y. Well, that implies there exists some other z, integer z, such that x minus y is equal to z n, but then that implies we can write y minus x as minus z times n, and that in turn, sorry if I didn't leave enough room, but that in turn implies that n divides y minus x. And by definition, that's what we mean by y being congruent to x. Is that n divides the difference. Okay. So if n divides with a positive number, it certainly divides the negative number with the same magnitude. So x congruent to y implies y congruent to x. So congruence mod n is symmetric. Yeah. So we just have to prove transitivity now. So now suppose x, y, z are in the integers, and x is congruent to y, and y is congruent to z mod n. We need to prove that x is congruent to z mod n. Well, by definition, that implies n divides the difference x minus y, and n divides the difference y minus z. That's by definition of the congruence relation. Any nice suggestions for a move to make here then, for a consequence to draw from those two statements? So congruence has been defined in terms of divisibility. So we're going to be using what we know about divisibility to establish behavior about the congruence. So is there any relevant thing we know about divisibility? The fact that if n divides x minus y and n divides y minus z, is there anything that we can draw on about divisibility that will help us here? Bingo, right? Linear combinations. That's a key thing about divisibility. Yeah. So which particular linear combination are you talking about here? Linear combinations of two things can be like any alpha times the first thing plus beta times the second thing. Can you be a bit more specific? Which linear combination? What? So we want to, we're trying to prove transitivity, so we want to get to a statement about x and z alone. And the statement that will turn into the congruence relation of x is congruent to z. So the property you're referring to is that if two things are divisible by n, every linear combination of them is also divisible by n. That's correct. Which is the correct linear combination to choose here? It's kind of the simplest one we could choose. Yeah, just to add them together. Maybe that's what you were thinking there. And if you add together these two quantities, it's kind of the most direct, straightforward linear combination of them, if you like. Well, you can see the y's are going to disappear because you've got minus y and y. And you'd be left with just x minus z. And that's exactly what we need to see in order to claim then that x is congruent to z modulo n. Because that's exactly how we defined the relation of the congruence. First thing is congruent to the second thing. If the difference, the first thing minus the second thing, is divisible by n. So x congruent to y congruent to z necessarily implies that x is congruent to z. Okay? So congruence mod n is transitive. So congruence mod n is a equivalence relation. That's correct. So now what we have is we have this picture of all of the integers. We have a partition of it, which we might draw a bit more systematically like this. We're taking our infinite set of the integers and we're splitting it up into a system of n subsets. And in each subset are all the numbers that leave the same remainder upon division by n. So in particular, in this subset here, the congruence class of 0, you've got all the multiples of n. And in the congruence class of 1, you've got all the multiples of n plus 1. Everything that leaves a remainder of 1 after you divide it by n. Okay. So on and so on for the other ones. Minus 1 in particular is located in this last relation here. Minus 2 is here. Okay. So this gives us a nice simplification of the integers. The integers, which is an infinite set, it suddenly now becomes a finite set of congruence classes. So next time, what we'll do, we'll look at this question: how do addition and multiplication behave on Z mod n? So this is Z mod n up here. Okay, so we'll be starting to answer this general question. And they behave very well, they behave very systematically. What they turn into is, so we know how to add and multiply integers. What it turns into is now we'll be able to add and multiply whole congruence classes put together. Okay. So we'll start talking about that tomorrow. Okay, okay, thanks for listening. That's it for this morning.